I want to look at, for sets with very few elements in them that we can just list, what does the Cartesian product look like? So what is it doing when we take the Cartesian product of two sets? What are the elements of that? So the fundamental thing that we can use is the definition, but not really. Actually, we should use the essence of Cartesian product, and the knowledge that everything in a Cartesian product is going to be a pair, meaning something we can write in this form, pair xy. So the essence of Cartesian product, this says a pair of things is going to be in the Cartesian product if and only if the first thing is in the first set and the second thing is in the second set. So what we're listing here are going to be all the pairs. They're all going to be pairs. So everything I list here is going to be a pair with two things in it, right? And the pairs that get to make it in here are pairs where the first position is something from the left-hand factor of the Cartesian product, and the second position is something from the right-hand factor of the Cartesian product. So for example, XA, that would make it in there. So would XB. So would YA. So would YB. So would ZA, and so would ZB. So what I'm doing here is, I have not proven to you that this equals that. To write a proof, I would have to, use the definitions. This is an equality statement, so I would have to, prove both inclusions, and it would be quite a long and obnoxious proof to write down. But this does end up being true, and I hope at least staring at this and our previous work with the definition convinces you that this is plausible, and this is what we end up getting. So given a set with 3 elements, well, actually we don't know that it's 3 elements until we know that none of these are equal to no one of these is equal to another one of them. So this is why I'm writing this up here. Assume that everything is distinct. So x, y, and z, distinct means no one is equal to any other. So this is several non-equality statements. I'm assuming that x is not equal to y, x is not equal to z, y is not equal to z, a is not equal to b, and in fact this even contains more non-equalities, like a is not equal to x, although that doesn't matter. Okay, assume they're all distinct, so that this really is a set that has 3 elements, and this really is a set that has 2 elements. Whatever that means. That's actually something we'll define later. Then, how many elements are there in the Cartesian product? 6, right? 6 because there are 3, to specify one element of the Cartesian product, you need to specify an ordered pair, and you have 3 choices for the first thing, right? Normally, how many choices you have for the first thing is how many elements there are of the first set, and then how many choices you have for the second thing is how many elements there are of the second set. So the number of elements of the Cartesian product was 3 choices times 2 choices for each of those choices, which is 6. So maybe now you're seeing why the symbol looks like a multiplication symbol, even though it is not multiplication. Okay, so no proof happened here. It was just intuitive discussion, but the hope is that this helps fuel the way you imagine things by understanding the intentions of what these things are supposed to do.